Good morning. We already had yesterday inaugural function, so I won't say anything. I won't say anything. Those who are not present, welcome today. There are 2-3 things. The DD need to be submitted to Safia along with the registration form. DD. If you have not taken registration form, take the form and fill the details, because that is to be sent to Government of India. After the course, you will get mark sheet, grade sheet, and also you will get certificate from Government of India. The mark sheet will have 2 units. You can take as a 2 unit, transfer to your mark sheet in your institute also. Right? This is the circular from Government of India. Every day we will have 3 lectures, which continuously, and there will be 2 breaks. 2 breaks. First break will have tea, second break will have lunch, and after that there will be a tutorial. Right? Any query, anything, there are 2-3 people here. There is Safia, there is Amir. Where is Amir? Amir. There is Sabir. Sabir, tell everybody here. You can contact this person or Barendra. Right? These are the people who they will help you, and you are always welcome. I'm here also. I will be also attending most of the lecture session. Right? Thank you. So, Professor Sasha.
Okay, well, good morning. Good morning. And, I hope okay, I'm going to present the course more or less quickly, like as the title. You already probably know that. And I would like to thank again the University Jamia, Millia, Islamia for inviting me to deliver this course. And I hope someday people will remember and say, I took a course, etc., etc. I think this is going to be bothering all the time. Let me get off the... let me kill this thing, because it's going to be bothering all the time. Sorry for this glitch. Sorry, otherwise this thing will be bothering me all the time. I'm sorry for this, but no. It's very intrusive, this Jamia thing telling you that you are out of the internet. Okay, so this is my email. You can hold on. Let me check something. No, I'm sorry, it's the wrong. Okay, sorry for this. Yeah. Okay. And this is my email, in case anybody wants to ask any question, whatever. Even during the course, like I have no cell phone here. Well, I have a cell phone, but I would not use it, would be very expensive, a Mexican cell phone. The roaming would be the size of the universe. But, but you can send me an email. Emails I can receive, even, and afterwards as well, okay? So, this is more or less an overview of the course. Like first, we have the first module. It's like the basic components of the course. Because the course is specially oriented to inhomogeneous models. Like we already know the Friedmann, Robertson, Walker models, and even simpler ones like Minkowski or de Sitter. They are homogeneous, and they are very simple. The idea of this course is to make you familiar with more complicated space-times that have more structure. So, but nevertheless, Module 1 will still review some basic concepts, like, for example, Einstein Equations. Is what we're going to see today. Basically, is Einstein Equations applied to Friedmann, Lemaitre, Robertson, Walker models. and I'm going to explain to you how different sources for these models can be considered. Then also I'm going to show you how Einstein equations work in general. See, because you'll see the contrast. Like Friedmann-Robertson-Walker is extremely simple. It's like a toy thing, very simple. But then I'm going to show you what Einstein equations look in general. So you'll see how much simplification is involved in Friedmann-Robertson-Walker. Then I'm going to show you an overview. This would be rather tomorrow. Like today, we're basically going to concentrate on Friedmann-Robertson-Walker models, because these are the simple stepping stones. And then I'm going to show you an overview of the different models: Kantowski-Sachs, Bianchi, LTB, Sekeres. And all this will be supplemented by examples taken from computer algebra. Like, for example, the idea is this 2 hours, sort of theoretical exposition. And then the third hour, it will be based on Maple sessions, so that you can see actually how these quantities are computed through Maple. Now, if you can follow this with your laptops. But don't worry, if you cannot do that, then the material will be left so that you can run them carefully at home. Also, after the third hour, that's the fourth hour after lunch, I'm willing to continue doing these Maple worksheets. And if somebody says, look, I don't understand you, I'm completely lost, or I would like you to explain again this thing or whatever, I'm here available for anybody during the day. Okay? During the day, after the 4 hours, if you still want to see me for asking questions, I'm here. Okay? Well, then this is module A. Then we're going to see more specialized subjects like LTV models, and to show you how these models can be worked out with special variables these variables really illustrate the properties of the models, and also illustrate in a very clear and precise and rigorous way how can you define inhomogeneity. Because inhomogeneity is not easy to define. It requires special concepts and so on, and so the models are ideal models to explain that, because these models have already a lot of structure that is not involved in Friedmann-Robertson-Walker. And it's important to see this transition from Friedmann-Robertson-Walker to LTV models. You can already see inhomogeneity working. Then we have a second part in which, once we have these concepts of how to characterize inhomogeneity in LTV models, we will apply it to several issues, like, for example, averaging of the space-time, and how can we relate to cosmological perturbations in different ways. And also we are going to see a dynamical system analysis, because dynamical systems, you know that they work very well for ordinary differential equations, right? Ordinary differential equations are ideally suited for phase space diagrams and critical points and so on. So what do you do when you have when your dynamical equations are PDEs, partial differential equations? Well, I will show you how can you handle that. How can you do dynamical systems when your PDEs are, when your dynamical equations are PDEs. In some cases you can do it. I'm going to show you how you can do that with LTV models. Then we go to the next higher step, which is Sekeres models. Sekeres models are powerful because they are no longer spherically symmetric. They are no longer spherically symmetric, and therefore the power they have to construct, to describe, to model structures, and I'm talking about evolving structures, non-spherical, really increases exponentially. So I'm also going to show you how you can work these models in order to describe, because there is a lot of ignorance, like a lot of people, especially among the astrophysicists, they believe that GR, they say, well, we have to do all this Newtonian. we want to model a bunch of superclusters. We have to do this with Newtonian physics. Why? Because GR is too complicated and it's not going to give us this. GR is good for toy models, or if you are going to work with black holes or neutron stars, then you use extremely powerful hydrodynamical codes which require a mountain of a computer and etc., etc. But if you just want to have something that has something in the intermediate area where a toy model is no longer appropriate, but you don't want to go to supercomputers, there is an intermediate range. They say, well, general relativity is not good for us. So that's why we use Newtonian physics, and then they say, well, anyway, velocities are Newtonian, everything is Newtonian, Newtonian, Newtonian. They are wrong. They are wrong, and I'm going to show you why. First, they're wrong because Sekera's models allow you to do this, to model evolving non-spherical structures, and it's fully relativistic. And also, they are wrong because we still don't know to what degree relativistic corrections will be important. We still don't know. They say, not important, not important. It's all Newtonian, all Newtonian, all Newtonian. And then I tell people of this type, how do you know? Have you done the calculations? Not necessary, not necessary. We know power spectrum, BAO, they always have a bunch of empirical explanations and so on. And they have very good empirical results, but the question is still in the air. To what degree general relativity gives corrections that are not being taken by people who continue doing Newtonian stuff? So Sekera's models will give you a hint of that. I'll show you how with Sekera's models you can describe non-spherical structures that are evolving. So this is further ahead. And then there's another, this course is not, I'm not going to see perturbations, and I'm not going to see detail on observations. This is a theoretical course. You have hundreds of courses and seminars everywhere in the world that will talk about the CMB, the BAO, all these things. I'm not going to dwell into that. Nevertheless, I'm going to show you how you can use this in homogeneous models to calculate observable quantities, to do supernovae diagrams and so on. But this will be essentially a review of the literature. I'm not going to be very deep, I'm just going to show you how it's done. And then, the final module is we're going to see other models. Like I'm concentrating basically on LTV and Sekera's models because these are the models that are more appropriate for cosmology. But nevertheless, there are other models, the shear-free, Kantowski-Sachs, and then to conclude, I'm going to show you how more general models can be devised, but not analytically. The Sekera's models are essentially as far as you can go with analytic work. And some of these models, even though there is an analytic solution, the analytic solution is so cumbersome that it's better to look at the models numerically. Nevertheless, you can look at the models numerically in more general conditions. Okay, so let's begin. Something important that is going to be valid throughout the course is the notation, conventions, and because there are differences of notations and indices and so on. And I'm in that sense a little bit old-fashioned. Say the metric signature is going to be minus plus plus plus. Yeah. Some people use it doesn't matter. Units, I'm going to take units where gravitational constant and speed of light are 1. So, so you will see numbers like 8 pi and 4 pi. Those numbers are going to appear. See, it's sometimes I'll put these constants, these fundamental constants, because they are interesting, important to to get the units correctly and so on. But normally, these units will be understood. Now, space-time indices. The letters A, B, C up to F, or even up to H, see A, B, C, D, E, F, G, H, will be four-dimensional. I have allergy to Greek indices. So no Greek indices will appear here. So the first letters of the alphabet are space-time. Space-time, that means they can run from 0, 1, 2, 3, 0 meaning a time-like coordinate. I will use different names for the coordinates, of course. Then indices I, J, K, L, M, N, the letters on the middle part of the alphabet are going to be space indices that are taken from 1, 2, 3. So this is important because sometimes people use notations that are completely different. So just bear in mind that A, B, C letters beginning of the alphabet is four-dimensional indices. Letters in the middle of the alphabet, especially I, J, K. For velocity, for velocity will always be a small u. And it's normalized to -1 because of the signature. Projection tensor is going to appear very frequently. It's a tensor that projects everything in the direction orthogonal to the four velocity. 3 directions orthogonal to the four velocity. And of course, if you have I don't have a pointer, right? Is there a pointer? Like in a broken antenna, as a pointer. So in case there is no pointer. Anyway, you see that tensor Q, that vector Q. If that vector Q, once projected with a projection tensor, and it's the same, that means that this vector is purely spatial, which means that contracted with a four velocity is 0. Please tell me, don't hesitate to interrupt if you don't understand anything, right? Because if you don't understand something and then say, well, I'm not going to say anything, then it's like a snow thing, you know, that's coming. First it's a little bit, some little doubt. Then it's a bigger doubt, bigger. So in case you have doubts, please don't hesitate to raise your hand and ask questions, okay? Now, symmetrization will be denoted, see, if you see indices with the round brackets, that means there is symmetrization with respect to these indices, right? And anti-symmetrization is with square brackets. The trace-free part, I will denote it like this, with a T, like, see, this is the trace of the tensor TAB. It's normally will be denoted as a mixed tensor with same indices. And then, this is another very important object that will constantly appear. The one on the below to the right is the angle, the angle brackets. The angle brackets, they denote projection towards a space-like projection, then symmetrization, and then removal of the trace, right? So, but this is it's an operator. You can define it as a tensorial operator that is acting on other tensors. If it acts on one tensor, it will take that tensor and make it space-like, then would symmetrize that tensor and then remove the trace. Okay. But it's very important because it will appear constantly. Many tensors that we are going to work with will be space-like, symmetric, and trace-free. So this is one way of making any tensor to be space-like, symmetric, and trace-free. It will appear constantly. You can always refer to Now, what I can do also is, see, this, I would suggest that you take notes, because the material that I'm going to be presenting is like a skeleton. If you only see the formulae 15 minutes after the course, then you'll remember them, but not 3 months after the course. So you should take some notes around. And this material, I can supply the PDF form. The PDF form for what you have here. And in fact, I can probably supply it in advance, right? See, the reason why, that you are taking this course and you already have the material. Why not? Because I had no idea what's your level or how are you going to respond. So instead of that, I'm going to do this, but in a few days. Once I have some interaction with you, because also this interaction determines the type of course, right? It's fake, this idea that maybe for people who are giving courses on management or business or whatever, they can do like this. Not me. No, I improvise in this case. I don't have a set course that it will work for everybody. So for this reason, you don't have right now in your hands this material printed. But now that I have some interaction with you, you will have it. I promise in a couple of days, you will have at least 2-3 days of advance, or at least the next day, so that you can study it beforehand. Okay? So, yeah, sure.
Can you define the projection tensor?
Sorry?
Projection tensor, can you define it?
Can I what?
Projection tensor,
Yes.
can you define it?
Definition. He wants to know what is projection.
Yes. Well, it's a tensor that is specially designed in order to project other tensors into a direction that is perpendicular to the forward velocity. See? It's the way it is constructed is by definition. In fact, it will be clear. It will be better understood along the way, because you will see how you can align coordinates with the forward velocity, but it's an important concept. We'll see that, because in general relativity, the notion of space and time is relative, of course, but nevertheless, when you have a vector field, you can use the existence of this vector field to define. If this vector field is time-like, then everything that is orthogonal to it can be used as a definition of space. That is, will be valid as long as you refer yourself to this time-like. So it's a tensor that is specially constructed so that given a forward velocity, you can project things perpendicular to forward velocity. Promise will be better understood. Okay?
Excuse me, can you clarify this, that trace and trace-free part, the second TAB, which brackets?
Where?
Trace and trace-free part, the
Yes.
second one,
With angular.
second term. TAB, HCADB. What is that notation it denotes? Which brackets?
Are you referring to this one?
Yes.
Yes, these are round.
Huh.
These are round brackets. These are symmetrization. See?
Okay.
See, these are angle brackets.
Okay, yeah.
These are round ones.
Okay.
So first, this is like an operator that is going to act. This is a tensor. It's completely arbitrary tensor.
Okay.
So first, you project this tensor with a symmetric part. This is a symmetrization, right? This is a symmetrization. This is following you just follow this definition and apply it here. And then here what you would be doing is contracting. This would be obtaining the space-like trace of this one.
Yeah.
See? And then, see, here you have the indices, the live indices. These are dummy indices. These are the live indices. It's just, the idea is, first, you see, look at this way. First, you contract with the H. That makes the tensor spacelike, in the sense that projected with a forward velocity is 0. Then you symmetrize it. This will make it symmetric.
Okay, yeah.
And then, see, this would be acting on this. Then minus, you remove, to all this, you remove the trace. See, you don't need to put a metric here because you have already made it spacelike. It's, are you people familiar with this type of notation, this type of tensors? No.
Most of them must be knowing.
Yes.
Most of them must be knowing. Isn't tensor is there?
Yes.
Well,
Maple, I think Maple will help.
Maple will help. See, here, once we go to the worksheets, Maple worksheets, you'll see them in action, these tensors. You'll see them alive. You'll see how they are defined and so on. Okay? Next is covariant derivative. I will use the nabla notation rather than the dot and the semicolon. But you'll see this. I will try to avoid writing the index on top when you use a nabla. But it's simply the contraction with a metric. And then curvature tensors, I will denote them with a curly R. Not with a Latin R, as is normal, because the Latin R, I will use it for metric function. So the tensors themselves, Riemann, Ricci, and the Ricci scalar, will be denoted by curly R. And then the Einstein tensor will be, it's a G, it's already here defined. And cosmological constant. Many times I won't write a lambda term, but of everything that I'm saying, you can always put a lambda term if you add a fluid with, in which the pressure is negative of the density. So sometimes I will include specifically a cosmological constant, but sometimes will not be there, but you can I'll show you how you can always add it. Okay? So these are the conventions. And now let's see this lecture, so today, to show Einstein equations, Friedmann Robertson. I'm going to motivate Einstein equations. And then Friedmann Robertson Walker models, and then we'll do some computer algebra workshops. So this is the activities for today. Okay? Well, Einstein equations and energy momentum tensors. So I'm going to motivate Einstein equations. Yes? This is like a 5 minutes course of GR. Like, hopefully it's understandable. Okay, we know from special relativity that every physical system can be described, you have a physical system, a scalar field, electromagnetic field, a bunch of particles flying all over, a gas, whatever physical system you have a class of observers that is looking at this, that is taking measurements of this physical system. Now, once you have identified a class of observers, if you have only one observer, it can be always one observer of a class of observers. But normally, we want to make statements about a class of observers rather than only one observer. Let's say you have a class of observers. We are observing the universe, you know. You can, if you just do like this, yeah, we already travel like 1 million kilometers in the time direction. So we ourselves are a class of observers, right? So there are many classes of observers, of course, but we use a tensor that is called energy momentum tensor to describe the physical properties of the systems we're taking under examination. And especially this energy momentum tensor is constructed in such a way that is divergenceless. That is, its divergence is zero. I think that I'm not saying something new for you. I think that everybody has taken a course on special relativity, right? Okay? So, now, these are the observers in space-time. We are like spaghettis in space-time, right? Okay? So, something very interesting, for example, if I do like this, I already traveled 300,000 kilometers in the time direction. When I'm going to travel 300,000 kilometers in a space direction? Never, it would take me years. So in space-time, we're traveling in space-time all the time. Even if we stand still, we're already traveled in space-time. So, but you have to make this into this sort of abstract jump, see? To try to think in space-time, see? Space-time, see, we are these spaghettis, right? And whenever we are moving along space-time, we're defining a world line whose tangent vectors are the four velocity and their time-like, right? And there is always hypersurface, at least locally, there is always a hypersurface that is three-dimensional, because in space-time, a hypersurface has to be three-dimensional, that we can identify with space. Now, once we have that, we can think of the stress energy momentum tensor, as what we're seeing is the flux of the four momentum in terms of the immediate three-dimensional surfaces that we're crossing. See, this is ourselves moving in space-time, and we always have whatever surfaces are like here, and here are three-dimensional, and they define volumes. So what we're seeing is the flux of the A component of the four momentum into the surface that is determined by the coordinate xb. And this, I'm sure you've seen this in special relativity, right? Doubts on this? Well, do you believe me that this energy momentum tensor is like a machine that concentrates energy density in the 0, 0 direction, energy flux in the direction that is mixed time and space, and momentum flux in the pure space-like directions? And this is always referred to a four velocity field. Why the four velocity? Because the four velocity is the tangent vector to the world lines of the observers. Right? We are the observers, so four velocity is a tangent to our world lines, and we have different types of surfaces that we have different types of surfaces at our disposal. See, here it is. See, here we are. Or velocity, and let's take coordinates. Let's take these coordinates, t, and here we have x, y, and z, right? These are our coordinates. This is our world line, and this is the four velocity, right? Now, we are looking at a fluid or at some field or whatever, and so we have four momentum in direction, in the flux, see, the flux of four momentum in the direction of x8, right? So here would be, for example, what we have is like T00 will be the flux, would be the flux of P0. P0 is energy in the direction of x0, which is Ct. So we would be seeing the T00 is the flux of energy, see, in this direction, in the time-like direction. But this flux is equivalent to an energy density. If you take the definition of a flux, like the momentum that flows per area, per time, it's a density. So this T00 will be energy density. Now, but you can also look at the flux, because the form momentum is flowing, not necessarily in this direction. It might be flowing in different directions. So you have a flow of form momentum along different directions, and this is essentially what will be giving you the different components of the energy momentum tensor, right? Are people familiar with the energy momentum tensor? Okay. So now, why do we want that the divergence is zero? Well, we want the divergence to be zero because, for example, we can construct, we already know that if the system that we are studying is a bunch of particles that are moving, say, we have the flow of rest mass density. It's just particles that are moving. And these particles carry their own rest mass density. So a system of this type, we call it dust. And the energy momentum tensor is constructed in this way. I mean, I assume that people know how to construct such a tensor from special relativity courses, right? Okay, so what happens if you, did you bring the formula?
In a few minutes.
Okay. If you take the divergence and set it to zero, you obtain something that is very familiar. You obtain the divergence law. Essentially is the conservation of rest mass. And it comes from this generalizes the Newtonian divergence law. So it should be correct. I mean, once you have a tensor, a stress energy tensor, and you take the divergence of that tensor and set it to zero, you should get something important, some conditions that have to be satisfied. Let's look at another example. For example, the electromagnetic field. Electromagnetic field, you can also construct an energy momentum tensor. You can, in fact, construct it from a variation. It's from the variation of the action. It leads you to this. There are several ways to arrive to it. And what happens if you take the divergence of this tensor and set it to zero? Well, you get Maxwell's equations, right? So the condition that the divergence of this tensor has to be zero is important. It's essential. It's absolutely essential, right? So whatever fields or sources that we're looking, we can describe them by an energy momentum tensor. And that energy momentum tensor, its divergence set to zero, will give extremely important conditions that have to be satisfied by the system itself. If you have, for example, a scalar field, then zero divergence will give you the Klein-Gordon equation, right? Or if you have a fluid, it will give you a generalization of the Euler equation and of the Navier-Stokes equation, right? So this is important. So what we have now, every source, given a family of observers, any source can be described by an energy momentum tensor. And that energy momentum tensor, its divergence has to be zero. This is what we have. Now, this is special relativity. I'm here, special relativity. No gravity, nothing, just special, plain, simple special relativity. Okay. Now, let's see what Einstein had two basic ideas. Einstein was, his time, this was known like after discovery of special relativity, so people showed that, you know, the papers by Einstein 1905 were on the motion of electromagnetic bodies. So this was known for electromagnetism and all sorts of systems. But then gravity, how do we incorporate gravity? That was hard, very difficult to do. Because Newton is not Lorentz invariant. And so that's very difficult. So Einstein had this idea. Of course, I never met Einstein, never asked him, hey, you really have, but as a humble follower of Einstein, I'm trying to sort of repeat what was in Einstein's brain. What were his ideas? I hope Einstein's ghost doesn't come here and says, no.
Sir, excuse me. Can I go back to the previous slide?
Sorry?
Can I go back to the previous slide?
What?
Previous slide.
Previous slide.
A previous slide? No. Okay. Not this one, but the one afterwards.
Yeah. After that.
Okay. This one?
Yeah.
Okay.
So this the flow mean and the time direction only you are considering.
Sorry?
In the example, the flow mean you are considering only time, not the spatial flow. The mass density you think the dust.
Yes.
Okay.
Yeah, dust is, say, you have particles, birds, and then you watch them. And suppose the birds, that's not true because the birds also have internal energy, but suppose the birds are, have only, let's suppose you're only interested in their mass, in their rest mass. So it's a flow of particles carrying rest mass. And you can construct I don't want to go into the detail because it would take some time, but you can construct this energy momentum tensor. Just looking at a bunch of objects moving, and they move along their forward velocity, and they carry the rest mass. Now, if you move along them, then you are in a comoving representation in which this tensor is extremely simple, right? But it's not necessarily that you are in a comoving, you might see them passing. If you are comoving with them, the only thing you will see in this reference frame will be the rest mass of this. That's why it's only rest mass density, see? Remember that that this description strongly depends on the form of your forward velocity, right? If you are comoving with some object, then your forward then see, for example, what is my forward velocity now in my system of reference where I'm addressed is 1, 0, 0, 0, right? Since all of you are static with respect to me, you have the same forward velocity, right? Because your word lines are like this. And so the forward velocity is extremely simple. It has the form 1, 0, 0, 0, right? Now, suppose I am in my reference system and I see you. Well, then your forward velocity will no longer be 1, 0, 0, because it will have to incorporate the fact that I see you moving. Right? And then my description of you as dust would also be more complicated. We'll see this. Okay? Well, Einstein. First, this is almost a cliche. In any Starbucks, you'll see the secretary saying, well, gravity is space-time curvature. Einstein said it. And everybody says that you don't have to see these ridiculous characters of Big Bang Theory. Everybody is saying this. Even politicians whose brains are not very evolved are saying this. So it is, well, what sort of curvature? Well, we think it has to be pseudo-Riemannian. Why pseudo-Riemannian? Because it has to generalize the pseudo-Euclidean nature of Minkowski space at small scales. See, all curved space, no matter how horribly curved they are, if you take a small bit, it's almost flat. All curved spacetimes locally flat. Now, among all possible curvatures that we can construct, it has to be pseudo, because it is generalizing pseudo-flatness. So Einstein should have thought this. Second thing, Lorentz invariance. I mean, if special relativity is Lorentz invariant, then the thing that will generalize that will have to be also Lorentz invariant, because it will reduce locally to special relativity. And also, the laws of this theory that Einstein was about or trying to invent had to be invariant under coordinate transformations. It is also, that's also a very strong physical requirement. Like if I'm doing a theory, like let's say I'm showing that that the universe is bouncing back, and I'm doing a theory, but then somebody tells me, yeah, but you are using very special, you are using the Sussman coordinates. They are very special coordinates. And I say, yeah, but with these coordinates it works. But then comes Gauche and says, no, but I want to use the Gauche coordinates. and he uses Gauche coordinates and the whole thing disappears. What would you think? Do you say Sussman and Gauche are a bunch of clowns? Right? So, for things to be solid, they have to be independent of the coordinates. Coordinates are extremely useful. In fact, without coordinates, we can't do anything, right? But your results should not be dependent on the choice of coordinates. You have to produce results that are coordinate independent, okay? And so that's an important requirement. Now, so probably Einstein followed this reasoning. First, we need to construct a curved spacetime. How we do that? Well, our metric, the Minkowski metric, in standard coordinates, rectangular coordinates, is very simple. It's the matrix with -1, 1, 1, 1 in the diagonal. So what happens if we simply take a metric and put horrible functions there? Well, you know that the metric defines local distances in a spacetime. So and it's connected with the Pythagoras theorem, right? We do small triangulations. So in a curved spacetime, these triangulations should very much depend on position and should be very complicated. So one naive way of generating a curved spacetime is to take a metric and make it horrible, make it complicated. What? Sine, hyperbolic of the cosine of the logarithm, or Bessel functions, throw whatever horrible things you want there. And of course, you think it's going to be curved, but be careful, because even the Minkowski metric, if you make coordinate transformations that are complicated, it will transform into a very complicated metric. But it will be related to the simple metric by a coordinate transformation. So you want to complicate the metric in such a way that it's not reducible to the flat space by coordinate transformations, right? But this is one way you generate curved spacetimes. But this is a sort of very sort of mathematical way. Now, that's fine, but then how do we find the equations that will govern the dynamics of this curved space? It's a space-time. We can define our space-time as curved or whatever. But what this space-time needs to have a dynamics. It needs to evolve. We need to make predictions of that. We need to relate it to scalar fields, electric fields, fluids, whatever. So what are the dynamical equations? So since all sources, we know from special relativity, all sources are described by some energy momentum tensor that satisfies the divergence-less condition, right? So what we need is a second-order curvature tensor that, meanwhile, we call it G. that will satisfy, that will be connected to the sources, right? Because this curvature tensor has to be sensitive of the type of sources. If you are a scalar field, you will produce certain curvature. Then out scalar field comes dust. You will produce another one, right? And if we put dissipative fluid, it will produce another one. So the curved space-time has to be very sensitive to the type of sources. All sources are described by energy momentum tensor. Therefore, this curvature tensor has to be proportional through a coupling constant. K, kappa is a coupling constant that we will determine later. How? By looking at the limit of the theory, the Newtonian limit. Now, for consistency, because we know that TAB is divergence-less, therefore GAB has to be divergence-less. But has to be identically divergence-less, because if we take divergence on both sides, we need to have a zero in one side. Because remember, when we take the divergence of the energy momentum tensor, it's not identically zero. What we obtain is a condition. Okay? Something that has to be zero, but is not trivially zero, right? However, so the tensor G has to be divergence-less, but trivially divergence-less, right? See, it cannot add extra conditions, because all the conditions are already given by the divergence of the energy momentum, right? I mean, these things, what I'm telling you, I've been teaching GR courses undergraduate for 30 years. These things are normal part of the course, right? Okay, so we need this condition, right? We need to find, you put an ad in the newspaper, a curvature tensor is required to show up at Dr. Gorsh's office. The tensor has to be second order and has to be divergence-free trivially. So all tensors are coming to see the interview. And then, see, the Riemann tensor is of fourth order, 4 indices. So it's not good. Now, but we need second order. So there is a contraction of the Riemann tensors, the Ricci tensor, and the simplest divergenceless curvature tensor that can be constructed with the Ricci tensor and the metric is nothing more, nothing less than the Einstein tensor. You can add also a cosmological constant. Why you can add a cosmological constant? Because the divergence of the metric is 0. So you can always add a constant multiplying the metric. See? But then this tensor is the simplest one you can construct with the requirements. You can construct more complicated ones, but then it gets very, very messy. But this, normally in physics, there's the Occam-Razor type of reasoning, that if you have two options, and both of them are logically correct, you take the one that requires less effort or less assumptions. So Einstein followed the Occam's razor, and he proposed his theory to have that form for this tensor, which, of course, he didn't call it, this is going to be the Einstein tensor. That was done after him. But he said, this is the tensor that is necessary, right? And then, these are Einstein equations. Einstein equations are Einstein tensor proportional to the energy momentum tensor. Notice that now some people, they say, geometry, curvature, horrible, horrible, that's stuff for mathematicians. I'm a physicist, physics. Throw away these geometry things, tell me. Well, for those people, you can say, this is a field theory. This is just a field theory, that's it. You compare it with electromagnetism. In electromagnetism, you would have something like this. You would have something like FAB equals some constant, comma, or let's do it like this. It's a field theory. Or you can, in fact, you can write also the equations. You can write the equation, Maxwell equations, in terms of a vector potential. So here, all what we have is a field theory where the potentials are tensors. You can conceive, see, in electromagnetism, this is a very useful idea. See, in electromagnetism, you have your potentials. You have the electric potential, which is phi, the electromagnetic potential, right? Okay? And then you have the forces. If you do derivatives of these things, you get forces, right? And then these are the potentials, and the derivatives of these are forces. And the very similar things happen. You can think of the metric as the gravitational potentials. If you derive them, you have forces, and the derivatives of the metric are the so-called Christoffel symbols, and they are forces. And the derivative of the forces are fields, right? And it's very similar to what you have in electromagnetism. The derivative of the forces are the fields, the electromagnetic field, right? So it's very similar. Except that, for example, in electromagnetism, the potentials are vectors. Here, our potentials are tensors, right? So it's simply a field theory. If you are very uncomfortable with this geometric idea, just tell yourself GR is a field theory in which the potentials are called metrics. For some obscure reason, they are called metrics, but think of the metrics as potentials, right? And so just it's the same as in Maxwell. In Maxwell, you are given Maxwell equations, and if you integrate them once, you obtain forces, electromagnetic forces, right? If you integrate those again, you obtain the potentials. So you have to perform two integrals of Maxwell equations to obtain the potentials. In GR is the same, right? You integrate the Einstein equations twice, you get potentials, which are called metrics. That's it. Forget about geometry or metrics or pseudo-Riemannian and that. Throw away that. But then what you have is simply a field theory. Okay? Now these are Einstein equations. The first thing we notice is that the Ricci tensor and the metric are symmetric tensors. And the energy momentum tensor is also symmetric tensor. But nevertheless, look at how horrible is the system. See? Look how it's written above, it's very compact because it's written in a tensorial form. And by the way, once it's a tensor, we know that tensorial equations are invariant under coordinate transformations, right? The components of the tensor may change, but the tensorial equation itself remains. Now these are Einstein equations, they look horrible. Bear in mind that each component of the Einstein tensor is a horrible, and I really mean horrible, algebraic combination of second-order derivatives of the metric. The metric is a potential, and the Einstein tensor is a field. So it's two orders derivation below, right? So it's really horrible. It's really, really horrible. The system we have, Einstein found a very complicated theory. Now, However, we are not now, for the time being, we're going to see that, the full complexity of that later. But now we're tired. So now we see very simple case. Cosmological principle. Cosmological principle, or sometimes it's called the Copernican principle, we assume that there are no privileged observers in the universe. Now, if you come to think very strictly, this is wrong, because if we are moving around in Mercury, the planet Mercury, we are a very special observer. And if we are moving in Pluto, which is no longer a planet, will be different. But the Copernican principle is meant for large distances. Because if we take the universe at very small scales, it's very complicated. It's extremely complicated, the solar system, or the motion of the galaxies, or several galaxies. So we erase all that. We take very large scales. How large? Let's say, if we take a scale of about 300 million light years, 100 megaparsecs, the universe at those scales becomes simple enough, right? It's the same, like if I look at one cell, it's going to be very complicated. But if I look at the hand, it's easier, right? And if I look at the hand like 100 meters distance, essentially all of me can be like a dot. It becomes even more simple, right? So we assume that the universe at large scales, that all observers should be equivalent, roughly equivalent, right? And so that means that every observer, we are all fundamental observers in the universe, and that means that all the observers, if they do a survey, a directional survey, they shouldn't detect any direction-dependent phenomenon, right? And if every observer can make this statement, then this is essentially the principle. We don't know, because how can we find out? I have to send this guy. He will have to spend 300 million years traveling, probably frozen. And then he would arrive 300 billion years afterwards. I would send him in some direction, and then he would come out of his ship and check that everything is the same in all directions, and he would say, yeah, Sussman was right. Now, he goes back, and Sussman is already, it's not even history. Sussman is absolutely gone by then. So there's no experiment or observation that can prove this. This is why it's called the principle. We assume it. And if things go well, it will go well, right? Now, if the principle is wrong, then sooner or later we'll... So, but this is very common in physics. Like when sometimes you tell people that are not in physics about this thing, they don't believe it. They say, how come? Principle, that sounds like religion or whatever. No, it's not religion. It's part of the scientific method, right? But then cosmological principle is one of such things. We assume it. So far it has worked. Now, if we assume the cosmological principle to be valid for every observer, we know that in reality it's only valid at large scales. But mathematically we can propose that to be valid at every single point. And in such case, what we obtain is the so-called the Robertson-Walker metric, which you have in front of you. This is, yeah.
Only the isotropy implies this Robertson-Walker model, or homogeneity is also needed?
No, say homogeneity is not, it's a corollary. If you have isotropy at every point, you obtain homogeneity. Homogeneity is very difficult to define, because isotropy is simply looking direction-wise in your point. But homogeneity is a statement on hypersurfaces orthogonal to the four velocity that you have no access to them. See? That's why the experiment that I'm sending this poor guy 300 million light years away, because he would have to go to another observatory to see if there is isotropy. Isotropy everywhere is what defines homogeneity.
Can we say isotropy implies homogeneity?
Sorry?
Can we say
From your hand, it seems quite simple.
Okay.
Smooth.
Yeah.
As. So
No.
what I mean to say is, what do you mean by isotropy at a point?
Yeah, no, that's an important question, because it is, we have to distinguish the mathematical model from the actual. If it happens at every neighborhood, then that space is homogeneous, right? Now, what happens in physics? In physics is that you, in the actual universe, this is not true, because if I'm here on India, and I'm looking at the moon, and I'm looking at the universe from the Earth, from any one point in the Earth, it's not going to be isotropic. It's going to be very anisotropic, because if I look in the direction of the sun, without protection, I can burn my eyes. If I look in other directions, I get much. You see, there is a direction dependence on your observations, right? So, obviously, the mathematical statement doesn't apply exactly physically. So how it applies when you consider what is called coarse graining, see? When you describe objects as far away, you remove this. When you consider local distances that are large enough, right? And then, of course, you might add there some statistical isotropy. So it's not perfectly isotropic, but it's more or less isotropic. See, one has to be careful between the mathematical model and the physics. Okay? The mathematical model is trying to describe the physics, but therefore we have to make simplifying assumptions on the physics as well. Okay? But that's it. Well,
Can we have break for tea?
yeah, let me just, I'm about to finish here. So, but you've taken courses on GR, no? No?
There are maybe some people.
Of the balloon, how do you see the other dots? They are receding from you isotropically, right? So the
Totally dd square minus.
suppose that this is our whirl line, and this is the whirl line of another cosmic observer, right? So we communicate by light rays. So when I receive a signal from that observer, I know that observer in a cosmic time Py, but I'm here in a cosmic time P0. So a statement on homogeneity would mean a statement of this observer here. But I can only have access to this observer here, because we communicate by light rays. So how can I be sure that all observers here are comparable to me? Very difficult. That's why I was telling you. I have to send somebody here to tell me that observations are also isotropic, and that person would have to come back. It's impossible. It's very. The point is, I make observations through light rays, so I have no idea what is happening here. This is why I have to make assumptions. And the assumption is a cosmological principle. I assume that these observers here, that are too far away for me to communicate with them, are seeing roughly the same type of universe that I'm seeing. They are not going to see identically the same one. But roughly, statistically, they are going to see the same one. It's an assumption. And once this assumption, the mathematical way to put it is that every observer, every one of these observers is seeing an isotropic world. See? Every one of them. If every one of them is seeing an isotropical world, then I am sure that all observers here will see the same thing, even though I cannot. But this is a mathematical result. If we assume that every single observer detects an isotropic universe, every one of them, then we can prove mathematically that coordinates exist that are aligned. Here I align the coordinates. This is my time coordinate, and these are my space coordinates here. Coordinates exist such that all quantities will depend on time, right? And this is why we call it homogeneous. But this is once the assumption is that every observer detects an isotropic world. That's the assumption, right? Everyone. If everyone detects an isotropic world, then I can align the coordinates so that time coordinates, the time axis is along the world lines, and the space coordinates are orthogonal to the world lines. And then every single quantity of physical and geometric interest will only depend on time. But time defined as the proper time along the world lines. You see? This is how the models are defined.
Yeah, here you have written A is a function of t, then it's a rho, no? Rho is a function of t.
Yes.
And this pressure.
Yes.
Okay.
Yes. Every quantity you can think.
Physical quantity. Yeah.
Or geometric.
Okay.
The Ricci scalar, the components of the Ricci tensor, of the Riemann tensor. Every quantity of physical interest will depend only on time, provided you use the time and space coordinates aligned with the observers. Okay? And this is now what happens when we do this? See, what happens is that solutions of Einstein equations for the Robertson-Walker metric. See, the Robertson-Walker metric, it has only 1 degree of freedom, the scale factor. You remember I wrote it there. So Einstein equations reduce to 2 ordinary differential equations. We'll see them now. Now, the solutions of Einstein equations are called Friedmann, Lemaitre, Robertson-Walker models. And why such a large name? Because these 4 men were responsible for creating the models. See, Friedmann Alexander Friedmann was a Russian astronomer, even though the name sounds German, but he was Russian. He took Einstein equations and assumed this cosmological principle and obtained the first solutions of this type with a source, dust. Dust being the source, obtained the first of these solutions. These are the Friedmann solutions, but they involve only a dust source, right? Then Lemaitre found all sorts of models with different pressures and cosmological constant, and we'll see that in a minute. But this was done by Lemaitre. Lemaitre was a Belgian monk. I think he was a Jesuit, and he did a lot of work in general relativity, but he published only in French, in regional journals in Belgium and in France, so he was not known. And Einstein was a bit dismissive of him. But actually his contribution is very important. Then who are Robertson and Walker? Robertson and Walker are an American and a British mathematicians. I don't know who's who, but one was American, the other was British, who explored the mathematics of these solutions. So the 3, and if you see, it's an alphabetical order, F, L, R, W. But happily, the alphabetical order coincides with the chronological order as well. Because Friedmann did all what he did in 1919, something very early, 1919. Then Lemaitre did his work in the early 30s, and the other two worked in the late 30s. So the models are called the FLRW models. Some people omit pour Lemaitre, keep pour Lemaitre, say FRW, but people should, you really give value to Lemaitre. I think Lemaitre did more important work than the other three of them. Now, these models, we are going to use there are several ways in which we can represent the metric. Essentially, the metric I showed you before and this one are related by coordinate transformations in space. Meaning space, when I say space here, I mean the three-dimensional hypersurfaces that are orthogonal to the four velocity. Because remember that space and time are relative. If I do a different arrangement of hypersurfaces, then space changes. But we are going to get along very well, without confusion, if space is understood by hypersurfaces orthogonal to the four velocity. Golden rule. Space is hypersurfaces orthogonal to the four velocity. Okay? Now, what happened? These are the equations. See, these are essentially they are. Two of them are non-trivial because I still don't have a pointer. So, does anybody have a broken antenna? Pointer. Anyway, are identical. The G theta theta and the GRR are identical. So you see these are the three equations. Now let's do a number counting. We have two equations for three unknowns. See? Because what we are considering as the energy momentum tensor of the models, we are considering what is called the perfect fluid. See? The Einstein equations that we have here are these ones. This is GAB, I'm writing it like this, equals kappa. The coupling constant is 8 pi G over C4. Right? But remember that I'm taking G and C equal 1. So it is 8 pi TAB. And what is TAB? This is the tensor that I am. And it's called the perfect fluid. And in matricial terms, what we have is this. We have this. These are Einstein equations. But they are only two because these three are equal. And these are equal. So essentially there are two equations, two differential equations, right? This form of this way of writing the tensor, I'm going tomorrow, I will look at these things, at Einstein equations in a general way, and we will see how these tensors are constructed. But meanwhile, you can think that in this coordinate system that is adapted to the cosmological principle, the energy momentum tensor is also very simple. And it has density it has energy density in the 0, 0. Remember the, yeah?
So you written H over there. So because for the hypersurface is perpendicular to the time direction for that, or what is the approximation that you written H over
Sorry,
there?
sorry. Can you
So
say?
you have written H over there in the expression.
Yes, yes, H, in these coordinates, H is very simple. In these coordinates, HAB is simply 0, 1, 1, 1. Okay? And the form velocity is 1, 0, 0, 0. See?
So what leads to write the H like that?
Sorry?
Kronecker.
Yeah, you can, yes, because you can write this one also in this form. You can also write it like this.
Yeah, that's right.
G.
Kronecker.
Yeah,
You can write it like this, right?
rho plus p.
It's the same, These are identical
Okay.
because of the definition of the H tensor,
Okay.
okay?
Yeah.
Now, in these coordinates, what happened here? Now, okay, so these are the two equations that we have to solve. Now, there are three unknowns for two equations. So, what we need is to impose an equation of state that will relate pressure and density, because the geometry is not telling us all the information. There's some information that will depend from the system, from the matter source. The matter source can be radiation, can be scalar field, dust, whatever, and we have to put this information, and this information is put in the form of an equation of state. See? Now, remember that there is this condition, the energy balance. This condition has to be satisfied. And this condition leads to this extra equation. Now, this condition, we can show that this is acting as an integrability condition of these two equations. So it's not really providing new information. See? Now, but it's nevertheless very useful. This equation here is also very useful, and we will use it. This equation can replace any one of these two. That is, we have really two equations that are completely non-trivial and independent of each other. They can be these two, or each one of these two and this one. These are trivial. Means that essentially these are only two, but we have nevertheless three unknowns for only two really independent equations. Now, if we want a cosmological constant, we simply replace rho and p above with rho plus p, or with rho plus lambda, and p minus lambda. Because we can always think of the cosmological constant as an extra fluid whose equation of state is p equals minus rho equals constant. See? So we can always introduce a non-zero lambda in this way. Now, these three equations are not very helpful in this way, but we can reorganize them algebraically. I'll show you in a Maper worksheet to obtain these equations. See? And this one, essentially, this one is rewriting, we can rewrite this one in this form. Now, look at this K0. K0 can be 0 plus minus 1. What does that mean? It means if K equals 0, it means that the space-like surfaces are flat. If K0 equals 1, it means that they have positive curvature. That is, they are hypersurfaces, hyperspheres, three-dimensional spheres. If they have minus 1, this means that they are three-dimensional spaces of constant negative curvature. Is what is called the pseudosphere. or hyperbolic sphere, or but this is what, because there are three types of three-dimensional hypersurfaces that can have constant curvature, these are the hypersphere, the plane, and the pseudosphere. And so this one, what we did is we rewrote this equation here, we rewrote it in this form. And this one we call the we call the Friedmann equation. Here I'm writing already a cosmological constant. This is a Friedmann equation. And then, if we write this equation, we do algebraic modifications of this equation, and we obtain this other one that this is the second derivative of the scale factor. So this is a sort of acceleration. This equation, the Ricciaruri equation, is telling us to what degree the expansion of the model is accelerated or decelerated. It would be accelerated if the whole thing is positive. For example, if the cosmological constant is very big, it will win over these two, and then the acceleration will be positive. However, if the cosmological constant is 0, and the pressure and density are positive, then necessarily is decelerating. But the sign here is negative, you can see that. And here, the energy balance, we simply wrote it in this form. Now, writing the field equations in this way is very useful for integrating them, and it also has physical meaning. Because this equation, the Friedmann equation, looks like an energy equation. We'll see that. And we are going to work with this too. Like, for example, integrating Einstein Equations. The most practical way is as follows. We take the Friedmann equation and the energy balance equation. This is the energy balance equation. So this is a logarithmic derivative of A, and this is rho dot, and here below we have P plus rho. And then the Friedmann equation, we write it in this form, right? This is the equation we have. Now, once we specify a relation between P and rho, then here we have derivatives of A and derivatives of rho. Then this one can be integrated, and the result of integrating it will be to have density as a function of the scale factor, right? And once we have density as a function of the scale factor, we substitute here, and we can integrate this into the form of this quadrature. And then we can obtain A as a function of t, right? And so we subjected to this boundary condition that A of 0 is 0. That means that the universe is expanding, right? A, the scale factor, is increasing. So let's go backwards. Let's look at the film backwards. Let's make the film go backwards. So scale factor in the past was smaller. We go further into the past, smaller, 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 smaller. Comes a point, it reaches 0. And yeah.
A gives the magnification.
Yes.
That to relative magnification, right?
Magnification of distance.
So at present, if we have no magnification, I mean that's what we are assuming, right? At present, no magnification. By as time goes, it will magnify.
No, there is magnification always. You just
from
compare.
our point of view, right?
Yeah, but you compare our magnification today with magnification before and afterwards. So you can say that maybe 1 billion years ago, 1 billion years ago, the magnification of distances was 1/2 of what is today.
Yeah.
And then in 1 billion years, it will be twice as what is today.
Yeah, that can be, of course. What is confusing me is at present the magnification should be this A should be 1,
Yes, yeah, because that's your standard, that's your rule.
Yeah, after all, it's a ratio, and
But that's arbitrary. That's yeah. You're right. We will do that. We're going.